Today I want to get into chapter 4. So this is about forces. So we have spent a long time, 3 chapters worth, talking about kinematics, which describes how things move, the way things move. Well, dynamics answers the big question that's been on your mind all this time is, but why? It's not that difficult to explain. It's because of forces. And here is a 1687 book published by Isaac Newton, in Latin actually, all about forces and how forces cause motion, and in particular acceleration, which now you're pretty much an expert in acceleration. Okay, this is another overproduced, nauseating video promoting sports, and I can't take it, so let's skip it. Here's section 4.1. Basically, this is getting you used to what forces are. So a force is a push or a pull. Okay, and there's a bird's eye view of 2 skaters. One is pushing a third, well, there's 2 skaters pushing a third skater. So one is pushing her forward and the other is pushing her to the side. There's F2 forward, F1 to the right. And so the net force, the total force on this skater is going to be off on a diagonal. So you can add forces like vectors. And again, you're an expert at vectors now. So all this work you've been doing for the past 3 chapters is really just to lead up to this chapter, I think. How can you measure forces? Well, one way, and you may have encountered this in practicals, is to use a spring scale. So a spring, it turns out, produces a force which is proportional to either how much that spring is compressed or how much it's stretched by. That's called Hooke's law. So you can use a spring to measure forces. Section 4.2 introduces what's called Newton's first law of motion. A body at rest remains at rest. Or, if it's already in motion, it remains in motion at a constant velocity unless acted upon by a net external force. So if you're going to change something from having a constant velocity, and that velocity might be 0, then you have to have a force from an outside object. And if you don't, then it just continues in a constant velocity. So there must be a cause for acceleration. A cause for any change in acceleration is coming from forces. And then there's something called mass, a property of a body to remain at rest or remain in motion. The loose term for that is called inertia, but the quantitative part of inertia is what's called mass, and it's measured in kilograms or grams or something. And moving right along, we have Newton's first law. Newton's second law is actually just sort of a more general version of Newton's first law. So what it says here is, first there's a lot of intro. Let's skip ahead. This is Newton's second law of motion in equation form, which is the acceleration of an object is equal to the net force acting on that object divided by its mass. So before that, they introduce a lot of stuff. But if you think about it, a special case of Newton's second law is when the net force is 0, in which case the acceleration is 0, and so you get Newton's first law. So I would say Newton's first law is almost like a special case of Newton's second law. Newton's second law is the more general one. So before that, they introduce a lot about what a net force is. So if you have a free body diagram, which it's part of your sketch is to draw a free body diagram, you put the object that you're thinking about, which in this case it looks like it's the boy in the wagon, and then you draw that as a dot, and then you draw all the forces acting on that object as vectors that are going away from that dot. So what's going on here? This boy is being pushed by 2 people. One's exerting a F1 and one is exerting F2, so you put both those vectors pointing towards the right here. There's also the boy's weight pulling down, so that's you draw that downwards. There's also the floor is pushing up on the bottom of these wheels here. You draw that, since it's an upward force, you draw it on this side. And the little f is some sort of friction force that's coming from, again, on the wheels from the ground, and so that points opposite the direction he's rolling. And then, since the net force here, if you add up all these forces, is towards the right, that gives an acceleration towards the right. So that's coming sort of from Newton's second law, so that the acceleration is a vector, the force is a vector, and the mass is a scalar. So the scalar mass doesn't change the direction. The direction of the net force always matches the direction of the acceleration. And then so there's some stuff about mass here. So acceleration is proportional to the net force, and it's inversely proportional to the mass. So basically, if you push with a force on a basketball, it accelerates a lot. If you push with that same force on a much more massive object like a car, it only accelerates a little amount. And that's not just due to friction, that's due to the fact that the car has a whole bunch of mass. It's also harder to slow down the car if it's coming at you. If a basketball comes at you, you just give a little force and it stops. If a car is coming at you, you give a force and it takes a lot to reduce its velocity because of its mass. Units of force, that's important. If you're using meters per second squared for acceleration and kilograms for mass, which are all the standard units we use in this course, the SI units as they're called, for Système International, then the force is measured in what's called newtons. And a newton is a derived unit, meaning it comes from other more fundamental units, kilograms, meters per second squared. 1 kilogram meter per second squared is what's defined as 1 newton. And it turns out you can convert it to pounds. 1 newton is 0.225 pounds. And then there's something called weight. So something has a weight in newtons, which is equal to its mass times whatever the local acceleration due to gravity is on your planet. So here on the surface of the Earth, this acceleration due to gravity is 9.8 meters per second squared. That's a constant. You multiply that times your mass, and that gives you your weight. And the weight is the same thing as the force of gravity of the Earth on you that's pulling you down. And that's going on all the time. And if you're not supported by something from below, you're gonna fall. So when the net external force on an object is its weight, so there's no other forces acting on you other than just gravity, that's called free fall. Okay? And that's what we were studying actually before. And I think the acceleration turns out to be the weight. Your net force there would be the weight on the top here, m times g. You divide it by m, the m's cancel, you get the acceleration equals g. That's why free fall has this constant acceleration. Okay, there's something about mass versus weight. In everyday language, since we live our lives always on the surface of the Earth, you can kind of convert the newtons of weight to kilograms, and it's 9.8 actually, but 9.8 newtons is the weight of 1 kilogram here on Earth. But keep in mind, mass is a more universal concept. If I went to the moon or into outer space, I would still have the same mass, but my weight would be very different. Standing on the moon, it's quite a lot less. Take-home experiment. What do bathroom scales measure? Turns out bathroom scale, let's just think about it, but I think it measures the normal force that's supporting you, which is kind of interesting. So there's some nice examples. Go through that. Rocket sled. This is Newton's second law is an important one, so this 4.3 is a good one to spend some time on. And lastly today is section 4.4 on Newton's third law. You knew it was coming, right? Okay, so Newton's third law is the most famous one. It's the equal and opposite thing, where the every reaction has an equal and opposite reaction. So they state it as whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. So example here is that the swimmer pushes off the wall. So the force of her feet on the wall is to the right. Well, the wall pushes her, force of the wall on her feet is to the left, and that's what accelerates her off to the left. So that's pretty straightforward. It gets a little complicated when you think about, here we have a professor who is pushing on a cart and accelerating the cart. And so if you think of object 1 as being the professor, object 2 as being the cart, then Newton's third law says that whatever force the professor pushes forward on the cart, there has to be an equal and opposite force on the professor pushing the professor backwards. So it doesn't seem right, because you wonder, well, how would the cart ever move? And so depending on which you define as the system, you only draw the external forces acting on the system. So if the system 2 is the cart, well, the professor pushes forward in the cart. There's some maybe friction pushing backwards. And the idea here is that the force that the professor pushes on the cart is greater than the friction, and so there's an acceleration of the cart. Well, then if you look at the system as being both the professor and the cart, well, these two forces here that are equal and opposite, they're not external forces, they're internal, so they can't accelerate that system. So you don't draw them on the free body diagram. You draw the normal force total on both the professor and the cart and their weight, And now you've got the force of the friction force from the floor on the professor's foot, pushing her forward. And again, a little bit of friction pushing backwards. And that's what accelerates the professor plus the cart. So you got to be a little careful with Newton's laws. And at the end of this chapter, it's talking about the gravity force between two objects. So that's not a very good fat animation for you to look at right now. It's not about gravity from the Earth. It's actually about this concept that any two massive objects attract towards each other with a universal gravity force. So I would skip that fat animation. 4.5 is on the normal force and the tension force. So we already introduced weight, the force of gravity. So now there are two forces that are really important. They come up a lot. The first is called normal force. It usually gets a letter N on it. So normal has two meanings here. Normal can mean ordinary, but in this case, normal means perpendicular to a surface. Okay, so you can have two lines that are perpendicular, but to have a line that's perpendicular to a plane, if there's no real perpendicular to that, we call it normal. So okay, so that's what the word normal here means. You've got a plane. It's a force that acts perpendicular to that plane. So, for example, this is actually what supports. If you put Bow Wow Chow on the table, the weight pulls it down, but it doesn't accelerate down because the table pushes upwards with a normal force. And what's interesting is that, I don't know if you can imagine standing on like a trampoline or something. The trampoline would bend down and stretch and then produce a force until it cancels your weight and it would stop you. And you may not think that a table would do that, but a table also bends when you put something on it, just a tiny little bit. Even a solid floor, when you're standing on it, always bends just a little bit, because the normal force is a self-adjusting force. It has to do with almost elastic constants in whatever surface you're standing on, so that it balances your weight. So it is important to distinguish. Weight is that downward force, that is M times G, and normal force, if the thing's at rest, is going to be pushing upwards with a force that cancels out the weight. So they're often the same magnitude when things are not accelerating, and when the surface is perpendicular to the surface is up. It asks you to be careful that the capital letter N is used for the normal force, and it's also used for the units newtons, so that's kind of a problem. And what's interesting here is that, remember, if you have something rolling down a hill, it accelerates horizontally, and it's been a little weird. You would think, oh, what's causing me to roll down the hill or to go down a skier to go down the hill? Well, it's gravity, but gravity just pulls in a vertical direction. So what is it that gets you going horizontally? The answer here is the normal force. So you have to draw a two-dimensional free body diagram where the weight still acts down towards the center of the Earth, and there's a friction, I guess, which they've put here, acting parallel to the surface, but the normal force acts perpendicular to the surface. So it's on an angle. And it turns out when you add up all these forces, if you take away friction or something, you get a net force, which is along the gravity plus the vector of the normal force, gives you a force that's in the direction of parallel to the plane here, and that's what gets you going. So it's actually the thing that carries you sideways is not gravity, it's the normal force. And one of the strategies here is you can take a force and divide it up into its components, and the y component and the x component don't always have to be like perpendicular, like vertically up and horizontally. You can tilt your axis if you're on an incline sometimes, so that x is parallel to the incline and y is perpendicular to that incline, in which case even weight is going to have an x and a y component. So that turns out to be a very useful problem-solving strategy. Next force is tension. So tension is a force that comes from a string or a cable or a chain or something like that. So example here, this person is grabbing on to a string which is holding up a mass. So the tension in the string is what pulls up on the mass. It also pulls down in this person's fist. So if you have a taut string, there's a tension which is an inward force that acts on both sides. So it's a pulling force. We use the capital letter T usually on our diagrams to represent tension. So lowercase w is weight, uppercase T is tension, and uppercase N is normal force. So, and there's lots of good examples of tension. Here's a tightrope where the tension is acting with a small upward component in these both directions on this person, and that upward component of the tension is what's balancing out the weight, and the horizontal components of the left side and the right side cancel each other out. So even if the weight is kind of small, the tension in a tightrope is very high, and so you need a strong tightrope so it doesn't break. And conversely, it's an old trick, is that if you have a chain connecting a very strong tree to your car, which is stuck in the mud or something, if you push sideways on that chain, even with a small force, it creates a very big tension force, and it's sometimes enough to pull the car out. So people have used tricks like that, physics tricks, to try to get their car unstuck. And talks here about the tension which is holding up this Golden Gate Bridge. And lastly, a little bit of reading about real forces and inertial frames. So all these forces we were talking about are real pushing and pulling forces, which involve two objects which are either pushing or pulling on each other. There are also what are called non-inertial reference frames, which lead to fictitious forces. So if you're on a merry-go-round, for example, going around and around, you can feel like you're getting pulled towards the outside. Well, that's because you're not in an inertial reference frame, and there's something called a fictitious force there. So you don't draw those on a free body diagram. And lastly, section 4.6 is a short one, giving you a couple of very useful hints for solving problems that involve Newton's laws of motion. So here is a sketch of Tarzan who's pulling on a vine or something. So you can imagine Newton's third law. If he's pulling downwards with his hands on this vine or rope, I guess, well, then there's a tension force pulling upwards on Tarzan. There's also the weight of Tarzan if he's suspended in midair. If you're interested in Tarzan, then, and he's pulling downward on this rope, then what you would say is that since he's pulling downward on the rope, he's the system. So this force that he's pulling down is not a force on the system of interest, since it is exerted on the outside world. He's pulling on the rope, and that's not part of the system. So you don't draw it on the free body diagram. All you draw is that upward force of tension and the downward force of gravity. So the outside world is outside the system, exerting forces on whatever you define to be your system of interest. That's an important tip. Another important tip is that in two dimensions, once you define your x and y axes, then the net force in the x direction is the mass times the component of that object acceleration in the x direction, and similarly the net force of the y components of the force equals the mass times the acceleration component in the y direction. So if you tilt your axes so that the object can only accelerate in the x direction, you know for a fact that there's no component of the acceleration in the y direction, then the F net y equals 0, meaning that your y components of your forces all must balance or cancel each other out. 4.7 is further applications of Newton's laws of motion, and 4.8 is just talking about the fundamental forces. So there's not a lot of very useful new information. It's just more like examples and little tips and tricks. So you should read through it, try through drag force on a barge. What they're saying there is that there's these two forces from, I guess, pushing forces from these tugboats, and then the water itself exerts this drag force on the boat. They talk about F-ap, applied force. I don't really know what that means. I think it just means the normal force because they're pushing. But anyways, you've got three forces. You try to balance those out. Tensions at different angles. So again, this is just about drawing free body diagrams really carefully, keeping track of all your components and balancing the forces out. If something's not accelerating, then the net force in the x direction is 0, the net force in the y direction is 0. That's all this is about. What does the bathroom scale read in an elevator? So the elevator might be accelerating, so the forces don't always balance to be 0. You sometimes think of the spring scale as being equal and opposite to the weight. Well, that's not Newton's third law. Newton's third law is saying that the force of your feet on the spring scale equals the force of the spring scale on your feet, right? And so this weight is the force of of gravity from the earth reaching up on you. It's a whole other force. So what you have to do is say that the net force is equal to the acceleration. So this mass times the acceleration. That's the idea here. So if you're accelerating upwards, then the upward force of the spring minus the weight has to be positive. You have to have, you're gonna have more weight on the scale if you're accelerating upwards. And the last example here is the soccer player it starts from rest and reaches a velocity of 8 meters per second in 2.5 seconds. It asks, what average force did he exert backwards on the ground in order to achieve this acceleration? So this is combining stuff from chapter 2 and now chapter 4. So you use chapter 2 stuff to figure out the acceleration. You know the change in velocity and the time, so you use one of those equations. Once you've got the acceleration, now you know the net force on the soccer player, and that's coming from the ground. And then you use Newton's third law to say that the soccer player is pushing backwards on the ground with that equal and opposite force. So you just get the 224. You just take that acceleration and multiply it times the mass of the soccer player, the 70 kilograms. And finishing up, section 4.8 is an extended topic, not super useful for solving problems, but kind of interesting, which is to say that there are, it turns out in physics, there's 4 very fundamental forces. So gravity, that long-range force, which is pulling us down towards the center of the Earth is one of these 4 forces. It's an attractive force, and the carrier particle is gravitons. So I guess the Earth is bathing us in gravitons, and that's pulling us down. The electromagnetic force is basically every other force that you're going to deal with in this course. The normal force, so when I push my hands against each other, well, the outer electrons in this hand are repulsive against the outer electrons in this hand because they're both negative, and that's what pushes my hands apart. Or if you're pulling on a rope, the tension force, it's actually electromagnetic forces between the molecules inside the rope is what's creating the tension, et cetera, et cetera. So it can be attractive or repulsive. I guess photons, which is actually light, is what's transmitting the electromagnetic force. And then the other two forces out of these 4 forces are called weak nuclear and strong nuclear. And these are forces within subatomic particles, okay? Like within the nucleus of an atom, you've got protons and neutrons, and they are attracted towards each other with this strong nuclear force. You don't have to worry about it in this course. Weak nuclear force is what creates things like beta decay. It has to do with these with leptons and things. So anyway, don't worry about those other 2 forces, but the point is that there are these fundamental forces that then create all these other forces that we have in our life. And there's this idea that maybe there's some grand unified theory in the future which will maybe unite all of these, and they'll all be different aspects of just one force. I don't know. But this is interesting. This is this idea of a field. If you have a positive electric charge and a negative electric charge, then we say everywhere in space there's an electric field. So if I put a little test particle somewhere, it would get pushed in the direction of the electric field at that point. And we can even have a gravitational field. So if I put a little test particle here, it accelerates towards the center of the Earth. So there's a gravitational field, even if there's nothing really there. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.